So about 3 months ago, I dropped a question in the community post whether any of you would be interested in joining an open crowdsourcing research paper with me. And so out of 555 votes, about 84% of you expressed your interest, and over 100 of you have posted your intention or your interest in joining this particular open crowdsourcing research paper initiative with me, where I'll be sharing with you an original data set. And so today is the day that we're going to share the original data set. And so the data set is going to be in the domain of computational drug discovery. Particularly, we're going to go to this database and then we're going to download a data set or several data sets. And the data set will be for molecules that have been experimentally tested to be able to bind or not bind to this protein called the Beta-Lactamase. And so I have already downloaded all of the data set from this database, and I've shared this as a zip file on the GitHub called Beta-Lactamase, which is the name of the repo. And then today we're going to perform a quick EDA of this particular data set. And then I'm going to provide some general ideas on how you could help to push this particular project forward. And so this is going to be probably one of the first open data set to be announced on YouTube. And I'm very excited to have all of you participate and contribute your machine learning, statistics, or any other expertise that you could bring to this project. And so I'm not sure whether there's going to be a lot of people participating, but if you're interested in sharing your Jupyter Notebook, your code, your models, please feel free to do a PR, and I'll try my best to read all of them. And those who contributed the most will be considered as a co-author of this particular research project. And then finally, we're going to write a paper together. And so for those of you who are biologists or chemists, you could also pitch in. And so I'll have to figure out again how we're going to write the paper together, whether on Google Docs, on Overleaf, or even right inside GitHub. Or you could also provide some ideas in the comments down below. And so let's get started and have a look at the data set. So go to this Jupyter Notebook. So I'm going to upload it into the GitHub repo shortly after I record this particular tutorial. And so let's start by downloading the zip file called Beta-Lactamase ChEMBL29.zip, which is in the GitHub repo right here. And so we're using wget to download it. And then after downloading it, we're going to unzip it. So it's about 1.35 megabytes in size. And now we're going to unzip the file. All right, and so let's see how many files there are. So let me count it. And then I'm going to pipe it into the WC command. And so we have 136 CSV files. And so remember this code? So I post this particular code in Twitter here. And so it's actually coming from this particular Jupyter Notebook. And so it receives quite a lot of attention here. And so it's just one way of repurposing this particular content. And so let's run this. So what this code would do is that it's going to use the zip file library in order to retrieve all of the CSV files that are inside the zip file. And so it will perform a query of the list of the CSV files inside the zip file. And then in a for loop, we're going to one by one retrieve the name from all of the zip file contents that are CSV. And then it's going to open it. And then it's going to use the pd.readCSV in pandas in order to read it. And then for each of the data frames that are created from the 136 CSV file, we're going to use pd.concat in order to combine it into a single data frame. And so let's do it. Oh, see what happens. Oh, okay. I have to rename the file name here. Let's do it again. All right. And so as you can see, it read in all of the contents of the zip file. And let's display the data frame, which is stored in the df variable. So this is the particular data set that we're going to work on together as a community. So you can see here that there are 71,973 rows spanning 9 columns. And so let's have a look at each of the columns here. We have the molecule ChEMBL ID. So this column is the unique identifier of the molecule. So each molecule will have a unique ChEMBL ID. And then it's going to have a corresponding canonical SMILES. So this is a one-dimensional representation of the chemical information, particularly the chemical structure. So it is a one-dimensional representation of the chemical structure. And you could also check out a prior video that I've made where you could convert the SMILES notation into 2D molecular fingerprint representation, which is essentially a molecular descriptor. And so molecular descriptors are quantitative or qualitative representation of each molecule. And so we are able to convert each molecule by taking the SMILES and then using a program called Paddle or PaddlePy, which is a Python library which wraps the Paddle program. And so what it will do is that it's going to take the SMILES notation here and it's going to convert that into a set of molecular fingerprints, which we can use to build a machine learning model in order to predict the bioactivity. Okay, so I'm going to tell you that in just a moment, which column is the bioactivity. Let's have a look further. And so the standard relation column is essentially telling us whether the data that we have got from the original research paper, whether they reported it as a finite value or whether it is a greater than a particular value. Like for example, in some papers, they might report a value of greater than 10,000 because 10,000 is the maximum limit from which the equipment can measure. And so they cannot obtain a finite value. Therefore, they say greater than 10,000. And so normally in a typical research project, we would delete those values because we're not confident which exact value they are. Okay, so if you would like to keep the rows, you might want to keep only those that have a equal sign. Okay, and so this is the bioactivity value, the standard value. Okay, so the standard value here, the values that you see, is the bioactivity value. And the bioactivity value will be represented in different types of bioactivity types. Okay, so here you can see that there's the KCAT, KM, there's the inhibition. And if you look further in here, in this column, you're going to see IC50 or KI. Okay, so typically we could decide on whether to use one of these bioactivity types. And normally I would use IC50 or KI. And in most situations, the number of compounds containing IC50 values are usually the greatest. And so therefore, I would just use IC50 because it normally accounts for the most data. However, in order to maximize the usage of all of the data, it might be a great idea to use the ChEMBL value. And so the ChEMBL value, normally it comes from the IC50 and KI. Okay, so it combines the value of IC50 and KI into this particular column and also apply a negative logarithmic transformation to it. And so values will be converted into the log scale. And so for the machine learning model building, you're going to use this as your Y variable. Okay, so if you want to build the machine learning model, which is going to be a part of this research project, then you want to take the canonical SMILES, you want to calculate the molecular fingerprints or molecular descriptor using a program such as Paddle or PaddlePy, and then given those molecular descriptors, you're going to use all of the descriptor as the X variables. And then for the Y variable, you're going to use the ChEMBL value. Okay, so that is one scenario. You're going to use the ChEMBL value as the Y variable. Or you could also compare it to another model where you use the bioactivity type to be IC50, but then you're going to use the standard unit. Okay, so you might need to filter IC50 values, and then you're going to use the standard unit of nanomolar here, and then you're going to use the standard value that are displayed here for the standard type of IC50, okay? So that we could compare the models between predicting ChEMBL value as the Y or predicting the IC50 values, okay? And so in the column here, target preference name, this is the name of the protein, okay? So these are the names of the protein. And the BAO label, it means the bioactivity ontology label. And so you can see here that it essentially describes the assay format of this particular data. And so you can see that this particular data was obtained from an assay format, or this was obtained from a single protein format. And so when you're building a model, you might want to separate the data on the basis of the different target proteins. So all of the data here comprising of 71,000 rows is going to be a mixture of different types of target protein, which I'm going to show you in just a moment. And so it might be a great idea to filter out the unique protein type and build an individual model for the different target protein. However, there is also another approach where you could theoretically use all of the data from all target proteins and build a single unified predictive model. And so that predictive model is called a proteochemometric model. And actually, I've talked about that in my 2.5-hour long video about computational drug discovery 101. And so I'm going to provide you the link to that lecture video in the video description. Okay, and so let's continue further. Let's have a look at the bar plot where I created the representation of the missing data or the non-missing data for the ChEMBL column. And so as I mentioned earlier, that we're going to use the ChEMBL column as the Y variable. Okay, so we want to see how many of the rows contain missing values and how many are usable. And so we could see that out of 71,000, about 64,000 contains values. Okay, so it is right here. So 64,000 contains the ChEMBL values. And so you're going to notice that when we display only the ChEMBL value, you're going to see the IC50 and also the Ki, okay? However, you're going to note here that some data entry are redundant, meaning that they are duplicates. So here you can see that there's molecule ChEMBL 777 and also ChEMBL 777 here. And you're going to see that there's a discrepancy in the value, right? Where one of the ChEMBL 777 has a standard value or IC50 value of 9, and it also has a value of 70. However, if you convert it into the log scale, then the value differ slightly between 8.05 and 7.16. But still, there is some variance that are present in these two data entry. And so what we would normally do is we're going to have to aggregate the molecule ChEMBL ID so that they become unique. And then we're going to remove the ChEMBL ID which contain a standard deviation above 2. And so if you calculate the standard deviation value for the ChEMBL value here for molecule ChEMBL 777, if the standard deviation value is greater than 2, you could delete this particular molecule from the dataset, okay? However, if the standard deviation is less than 2, we're going to keep it, but then we're going to merge it into a single row, okay? So if it has a duplicate here, but you're going to see that it has many duplicates, right? There's 1, 2, 3, 4, okay? So if the standard deviation is less than 2, we're going to keep molecule ChEMBL 777. However, we are going to merge it into a single row. And then in order to do that, we could calculate the mean value or the average of that. And so you could calculate the average of the ChEMBL if it has a standard deviation less than 2. But if it has a standard deviation greater than 2, we're going to delete the entire ChEMBL 777 from our data set. Okay, so let's proceed further. So as I mentioned previously, you could aggregate the data by performing this group by function. right? And then it's going to group the data by the molecule ChEMBL ID. And so this will become unique. And so in order to figure out which one contains multiple values, meaning that which one has redundant values, you could also calculate the standard deviation. And if you see that it has a standard deviation, it means that there are duplicates in here for this particular ChEMBL ID. But if it's a NaN, it means that there is no duplicate. And so if there's no duplicate, we keep it. But if there are duplicate, we're going to apply the less than 2 standard deviation as the cutoff. And so after you have applied the standard deviation of 2 as the cutoff to keep the redundant molecule, but then a single copy of that, you're going to merge that into your entire data set where there is a single value. Like for this one, when you see that there's a NaN value here, there's a single value, so there's unique. And so we're going to keep that anyway. And so once you merge the unique value from the redundant value, if that's not confusing to you, then we're going to merge that both data together. Okay, and so these are just some testing code that I've created. So feel free to modify this. Okay, we're gonna skip over to this one to run it. So for this one, I've just printed out the number of unique ChEMBL ID versus the total number of ChEMBL ID. And so here you can see that the first printed value is the number of unique ChEMBL ID. And so for this one, we selected the molecule ChEMBL ID and then we applied the unique function to it. And for this one, the total number of ChEMBL ID, we applied the length function to the df. And so we got a total of 71,000 rows. And then we also tested whether there are any missing ChEMBL ID, and the result says no, there's no missing data here, right? Let's see. What is this one? Okay, so I guess I just tested the code, and so you could feel free to delete this one as well to run this code here. Right, I think I wanted to make a plot comparing the unique and the redundant data. So please feel free to help me complete this particular code cell, and if you want, you could help to do a PR to the GitHub repo. All right, and so earlier on, I talked about the different target proteins that are in this particular data set. And so if we do a top 50, you can see that the x-axis lists the name of the target protein, and the y-axis lists the number of rows for each target protein. So you're going to see that the first one, called Beta-Lactamase AMP-C, it contains more than 60,000 data samples. And so recall that there are 71,000 data samples originally. And so this one accounted for nearly 80% roughly of the entire data set. And so it might also be a good idea to compare this particular data set with the rest, okay? However, there are other issues to consider, like for example, the first target protein contains nearly 80% of the entire data set, whereas the others contain a smaller portion. So it might be interesting to investigate how this imbalance could be handled. Like for example, you might have a unique approach that could handle such imbalance of the data set. And so I would love to see all of the creative solutions that you come up with. Right, so let's have a look at this one. For this one, we printed out the top bioactivity units, so we're going to visualize it. So you're going to see that roughly 60,000 contains data as the potency, and only a couple thousand here contains the IC50 value, and the Ki and the Kd, okay? And so this is from the bioactivity units column. Let's have a look here for the bioassay ontology, the BAO label column. So roughly, yeah, 60,000 comes from the assay format. So I'm guessing that this one comes from AMP-C, the one with the most data, right? So it's 60,000 corresponding. And also here, assay format, potency, and AMP-C. It's probably the same data set. Okay, let's have a look here. What is this? And so for this one, we've created a histogram for the ChEMBL column. And so you can see the distribution of the values. All right, and so the challenge here is to create a Jupyter notebook where you perform an exploratory data analysis of this data set. And what would be useful is you could apply the Paddle software or the PaddlePy library in Python. And I've actually created a video about that, so you could find a link in the video description. And so you could convert the SMILES notation into molecular fingerprints, and then you could perform exploratory data analysis on that. And some ideas that you could explore is to do stratification of the data set by the bioactivity class, meaning that you take the ChEMBL value and then you apply a threshold. Like for example, let me jot it down here. So if you take the ChEMBL values and then you could convert this into the qualitative label, like for example, if the ChEMBL is less than 5, you could call this to be, you call it as an inactive molecule. However, if the ChEMBL values is greater than 6, you're going to call it active molecule, which means that it has good activity. However, if they are between 5 and 6, you're going to call it intermediate. And so you could perform exploratory data analysis by comparing the 3 groups here: inactive, active, and intermediates. And for each of the groups here, you could compare the molecular fingerprints that are created. You could also compare the distribution of the histogram of the ChEMBL values. You could compare the molecular weights for each of the group. You might be able to discover whether active molecule prefers molecules that are big or molecules that are small, or whether inactive molecule are big or small. Or you could also explore other parameters of the molecule, whether the solubility is polar or apolar for the active or inactive molecule, or even the intermediate as well. And so please feel free to use your creativity in performing the exploratory data analysis. And you could create a Jupyter notebook and upload it to the GitHub. You could share the link to me as well in the comments down below. You could also do a PR or a pull request and share your code or solution or comments. So I might also upload this particular data set to Kaggle, and I'll provide you the link to that also in the video description. And if you would like to, you could also contribute the Jupyter Notebook over at Kaggle as well. And aside from doing EDA analysis, you could also build machine learning models predicting the ChEMBL value. You could make a regression model predicting the ChEMBL value, or you could make a classification model classifying whether the molecule will be inactive, active, or intermediate in a multi-class classification. Or it could be a binary classification where you compare between active and inactive. Okay, and so aside from using Paddle as the molecular descriptors, you could also explore the use of other representation of the molecule. For example, you could convert it into a molecular graph, and then you could apply deep learning to build the model. You could make it into a image, and then you could build a convolutional neural network. You could also represent the molecule as a string of text, and then you could use long short-term memory LSTM to build the model. And so as you can see, there's so many approaches that you could do with this particular data set. And I would love to see all of the solutions that you guys and gals come up with. And we'll see how far we could get this open research project going. And so I might also create some videos in the future to showcase some of the solutions that you come up with, which might also be some guidelines or ideas or inspiration for other participants of this open research project as well. And so finally, when we write this paper and get this into a manuscript form, contributors who contribute the most to this project will be considered as a co-author. However, it's going to be merit-based, and I hope that this will be a fun initiative. And if you like it and you would like to help to promote this, please give it a like, please share the video, and subscribe to the channel for future updates and videos. And as always, the best way to learn data science is to do data science. And please enjoy the journey.